Hello.
Hello.
How
Wait,
are
this
you?
one. Can you hear me?
Yeah, I can hear you. Can you hear me?
Yeah,
Yeah. How are you?
I'm all right. I am struggling.
Do you have a test on this on Friday?
Yeah,
I see. Um,
and I am not well prepared.
is it on the problems here, like the workshops you sent me, like the two workshops, or are there any like more material, or is it just like these two workshops that you sent me?
Um, you have the textbook by, let me see. Let me see the name of the textbook. It doesn't tell me the name of the textbook.
Oh, I see. It's okay. We could get started on the workshops, and then for the other like sessions like this week, we
Yeah.
could go over the textbook stuff when we finish this.
Okay.
Yeah. So, let's see here. Do you understand the pKa stuff or here, or we could go over from the beginning, like if you like don't understand the pKa stuff
Uh,
for the
I'm guess
first. Uh-huh.
I'm guessing it's kind of asking like why those split ABC is there. So it's like why when you the hydrogen for like 50 is like more basic compared to the
Mm.
hydrogen below. And
Yeah,
then
that's right.
for this
Uh-huh.
one, I put dieckmann. It basically forms it's a weak acid because it forms a strong base, and then the ones between A and B, those are allelic.
Yeah, that's right. That's right. Where the hydrogen that they are looking at are these hydrogens right here. And
Yeah.
when we draw the conjugate bases of that, right? Like let's say some random base deprotonates that hydrogen, we're gonna get
Mhm.
this conjugate base right here with the lone pair on that carbon that lost the hydrogen.
Yeah.
Right. And you are correct. Like this position here is allylic, meaning that this lone pair here is more stable than this lone pair because it could do
Mhm.
resonance with the double bond right here.
Yeah. And then for the C cut, I put the ones under C, they form enolates.
You know, say let's see NO2, right, plus and then CH.
How you been doing?
Oh, wait, what was that?
I was asking how you been doing. We haven't talked since like high school.
Oh yeah. I've been doing well. I know, like the last time was like Mignato's class or something, right? Like calc.
Yeah, Mignano or Bit.
Yeah, in Brit class too. I remember. I
It's
know
been
it's
a
been a while.
while.
It's been like 5 years or like 4 years or something like that. I
Yeah.
think it's
And
been a
here you
while.
are, old chem tutor. Your page looks amazing.
Yeah, thank you, thank you. See.
I wish I went to you when I started OChem, so I wouldn't be here.
Oh yeah. When did you start OChem?
I technically took it 3 years ago, but then I was true because of mental health.
Oh yeah, uh-huh. Yeah, mental health
So
is really important. Like if you're like not there, then like it's really hard to focus and
yeah,
do work. Like
and
yeah.
now it's my last semester, and I need a B in this class, and I am quite lost.
Let's see. I'm trying to figure out like the bond line structure of this thing right here. CH2, CHOH. Oh, I think it's just OH right here. OH, like that.
Yeah.
Okay. So the very first thing that I like to do to determine like the acidity of things is I like to like draw out the conjugate basis where we know that we just get rid of that hydrogen and
Hmm.
add a lone pair or a negative charge on whatever atom it was on.
Yeah.
So here are the negative charges, right? Where we see that this has a lower pKa, meaning that this is more acidic. And if it's more acidic, it means that this will be a more stable conjugate base. The reason why this would be a more stable conjugate base is because when we draw the resonance form, the other negative charge is going to be on an oxygen atom. And we know that oxygen is more electronegative
The
than,
nitrogen. Oh, the carbon.
yeah, that's right, than carbon, which is why this resonance structure here is more stable than that resonance structure because the negative charge there is more stable at the oxygen atom than the carbon atom,
Okay.
which is why this is a lower pKa. Oh shoot, did I skip over B? Oh shoot. That was accident. Let's
Oh,
see.
for B,
Mhm.
it's because I was bringing it up, so I
Oh,
skipped over B.
oh, I see,
B,
I
I
see.
put it's oh, it's because when you remove that hydrogen's an alpha hydrogen, which is
CH2,
slightly acidic.
H2, oh, have we removed that hydrogen? Yep, alpha hydrogen, which is able to do resonance and give that negative charge on the oxygen as well, right? And over here, this can do resonance, like it could do a lot more resonance than this other one, but the reason why this is not as stable is because you know how this is a benzene ring that is aromatic?
Mm-hmm.
When we do resonance, we
It's
are
gonna have
breaking
like
the,
four structures.
yeah, we're gonna break the aromaticity, like which is not stable because we wanna
Mm-hmm.
keep the aromaticity. Right. Mhm. Right. Breaks aromaticity, which is not good, which is why this is not stable, which is why this is at higher pKa. But this is okay because it's at the alpha position, and when we draw the resonance structure, the negative charge is on oxygen as well, which is more electronegative. And it doesn't break any aromatic system. Mhm. Let's see. Ready to move on to the next questions?
Yeah.
Okay. See. Explain why the alpha protons of an ester are less acidic than alpha protons of a ketone by around 5 pKa units. So let's say they are comparing.
Isn't this uh so I already did this worksheet. I just didn't get it checked yet.
Mhm.
Isn't this basically what you explained on the previous page? Because the ester, when you take the hydrogen, the resonance structure, there's one where there's the C double bonds with the other oxygen, and then there's a plus charge on the oxygen, and that's less stable.
Right. So when we draw the resonance structures here, the oxygens will have negative charges. Both oxygens will have negative charges.
Yeah.
Right. So these are the resonance structures here,
Mhm.
but you notice how there is an oxygen next to the carbonyl of the
Yeah.
ester here? That oxygen right there. Oh, is that what you said? Like it could do resonance right here?
Yeah. And
Yeah,
then
yeah, yeah, yeah.
because that resonant form is less stable than basically the enol form of the ketone.
Yeah, that's right. Because yeah, you're correct, you're correct. Because this is competing with the resonance here. There is
Mhm.
less resonance power of this negative charge. Because there's a competing oxygen that's doing resonance with the carbonyl as well. Whereas in the ketone, there's no competition. There's no oxygen doing resonance, which is why this negative charge here has all the resonance power to itself for this
So does
carbonyl.
that mean in general, if something has more resonance structures, it's less stable to something that has less resonance?
Not always the case, but it depends on like what the system is. For example, like let's say we have like for example in A, right? Uh, this one here had more resin structures and it was more stable than this one with no resins at all.
Oh yeah.
Yeah, so it depends on what the system is and if there's any competition at all. In this case,
Mhm.
there were no competition, and in this case, we were breaking the aromatic ring. In this case, the same amount of resonance, but the factor here that we kept into account was the electronegativity.
Negativity.
Yeah,
Okay.
that's right. And then this one was the competition of the resonance of the carbonyl here.
Mhm.
Mhm.
And then for B, I put the 2,4 hexa. hexane dione. The enolform is more stable because it forms a H hydrogen bond and it's also conjugated.
Mm-hmm. That's right. That's right. Because when we deprotonate that, we're gonna have a negative charge. So first, this gets deprotonated
Mhm.
into the negative charge, and the negative charge can do resonance there, and then
Mhm.
this could grab some kind of hydrogen to get to this enol form that can do that hydrogen bond, like you said. That's correct. Yep.
Yeah, and it's also conjugated.
And it's also conjugated. That's right. Conjugated. H bond here. Conjugation here. And but the isomeric diketones 3,4 hexanedione.
And then for those, is it basically because they can't?
3,4. Yeah, like there's no there's no like carbon in between them for the 3,4 hexanedione. Let's see the 2,5,1. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. Yeah. There are like alpha carbons in between them,
But they're
but
too far.
yeah, they're too far apart to be conjugated and do H bonds with each other. So mhm. Too far. That's good. That's good. Nice. Let's see. Next one.
This was where I started getting confused.
Oh, let's see. Why acid catalyzed bromination of two pentanol stops at the mono bromo derivative? So let's draw out two pentanone.
Mhm.
1, 2, 3, 4, 5. Okay. And they're asking for the acid catalyzed bromination where we do like BR2 under acidic conditions.
Does it matter what acid you use, like sulfuric acid, uh,
Mm.
H3O plus or HCl? Like, does that matter?
No, it doesn't matter. Any strong acid would work here.
Okay.
Right.
And what conditions would they matter? Because I think
What
one of my biggest issues is
uh,
mainly like solvents and reagents.
oh yeah, so weak acids would probably not do this reaction here.
Okay.
Yeah. Let's see. Okay, let's see. Let me see the mechanism here really quick. Let me check the mechanism of this.
Isn't it the oxygen attacks the one of the H from the acid and then it
Hmm.
forms the enol form
Yeah, that's right. That's right.
and then the conjugate base from the acid comes and attacks the alpha hydrogen and the electrons from that hydrogen forms a double bond with the carbon and the carbonyl.
Yep, like that. And then we do form the eno like you said.
Mhm.
Then we do
Can I ask how you studied for OChem? Did you just keep watching videos and practicing?
yeah, I watched videos and I use this website called jochem.io. Let me type it on the Zoom chat right
Yeah,
now.
you sent it to me on Instagram. I checked
Oh,
it out.
really?
His videos are very like nice and easy to understand.
Yeah, I watched those videos and also when I took OChem, it was like during like the lockdown
Hmm.
period. So I like had open notes, open
Oh,
internet as well for like 2 quarters of it. And but when I went for the in-person OChem
hmm.
class, I failed my first like midterm because I didn't know how to study for in-person tests because I was so used to online. So then I had to like drop all my other not drop but like ignore my other classes and just focus all on OChem.
Hmm.
And then I
Did
watched
you pass that
videos.
semester?
Yeah, I passed. But I thought I was gonna fail after the first midterm, but I might have come back
Yeah, I
after that.
bombed my second midterm, but
Oh
he
shoot.
drops one, so I'm hoping I do well on this one, the next one, and the finals.
I see that there's 3 exams and the final.
There's 4 exams in the final. That was the first one I did okay on.
Mm.
I got two multiple choice wrong, even though on the test I marked the right one, but in the Scantron I marked a different one,
Oh no.
and I got that's 10 points off right
Uh,
there.
I know that's a common mistake.
Yeah, I did the same thing in physio. I was that one question would have given me the A,
Oh
and
no.
I would have been excused from doing the like makeup thingy.
Oh no. That's so sad.
Yeah,
But now you know to like check your
yeah, it was like
answer.
now it knows. But then for OChem, because I don't understand as well, I usually take up the whole time. Physio, I'm more well studied for because for subjects like physio, econ, and the other classes I'm taking, a lot of it is like real life applications and things that can apply to me or things in real life. And
Yeah,
it's easier
yeah,
to like understand. But then OChem is like,
yeah. Like, what's going on, mumbo jumbo?
yeah, it's like I can't apply this to anything because I don't look at stuff in real life and like, oh, I see the atoms.
Yeah, yeah.
Okay,
Let's
what
see.
have you drawn here?
Uh-huh. So this is showing you here, like how we protonated the carbonyl oxygen and that
Yeah.
becomes positive charge oxygen right there.
Hmm.
Then I just used the conjugate base to deprotonate the alpha
Yeah.
um carbon to make the enolate
It
here.
deprotonates the alpha carbon on this side because it's more stable than the hydrogen on the left, right?
Yeah, that's right. This enolate here is more stable than the one on the left. Mhm.
Hmm.
Right. And you know how there is a negative charge on this carbon right there when we do, like, let's say this resonance structure, like we make that double bond there, and then we create
Which the
a
electron, yeah,
lone pair of electrons there, right?
yeah.
Um, this negative charge here is the nucleophile that's gonna attack this bromine and kick out the other bromine.
Hmm.
When we try to do that again, right? Like protonate this oxygen with the acid, like we did in the very first step, and then we
Yeah,
try to make the enolate ion here. Imagine there's a negative charge right there, right?
yeah.
This negative charge right here is stabilized by this electronegative bromine, because this electronegative bromine is withdrawing or pulling the negative charge, making it more
Mhm.
stable because it's more delocalized.
Yeah,
If it's more stable, it won't be able to attack another bromine. It will be
because it's
weak.
being pulled towards the bromine instead of trying to attack something else.
Yeah, that's right. That's right. Uh-huh.
Okay,
Yeah. So that's the reason why in acid catalyzed bromination, it stops at the mono bromo derivative. We don't do a poly bromo where we add like multiple bromines, because it will not create
because of what
um
you just said, right? Like,
yeah, yeah.
the electrons won't be able to attack.
Yeah, the electrons are stabilized. They won't be able to attack. Uh-huh. That's it.
Do you, I guess, draw this again, but base catalyze?
Yeah, yeah. Let's do it again, but base catalyzed, and then I'll show you why base catalyzed is poly. Like if we do multiple
Hmm.
times, say we do Br2, NaOH, let's say. So in this case, we don't have any acids. This NaOH is just gonna straight uh deprotonate that alpha carbon and create
Hmm.
that enolate ion right there.
Yeah.
And when we know that this carbon here, it has a negative charge when we do the resonance, where that negative charge is just going to go and attack the Br2
Hmm.
and kick out the other bromine. That's going to give us
The
this,
same product as earlier,
yeah, the same product as earlier. But
but
in this case, right, we could keep going on because I'll show you why. Let's say OH minus, do that, that. we have this, and then Br. Okay. Which structure do you think is more stable? This structure or let's say this structure or
Is it the top one?
yeah, it's gonna be this one here, like because this is the like the equivalent of that, but in basic conditions. This top
Mhm.
one is more stable because it's neutral, and because it's more stable, it's a weaker nucleophile. Since this is less stable, this is a better nucleophile. It could keep going on, because since this is less stable, it would want to attack another thing, right? Because here when we have a negative charge here, that is already stable because it's like its enol form is neutral in
Mhm.
acidic conditions. But in this case, we don't have an enol, we have an enolate, which is the deprotonated form of the enol.
Okay.
That is less stable than the neutral version, and if it's less stable, it's more reactive, which is why it can react again.
Is this similar if the compound had a plus charge instead? Like as long as it has a charge compared to neutral, it's more reactive.
Oh, if it had a plus charge, then that wouldn't be a good nucleophile,
Nucleophile.
right?
But
Because
then can
nucleophile.
something else attack it? Like can another BR2 come and attack the plus charge?
Oh, if we had a strong base or something else, it could deprotonate it because like if there was a positive charge here, OH2 plus, then that would be an acid instead. Like a base would just come in and deprotonate that to make it neutral, to go back to the neutral version. Right? Like let's say we have this OH2 plus positive charge right there. Something like water
Mhm.
or some other thing will just come in and deprotonate that structure to make it um
OH.
OH and neutral again, to make the enolate again.
Mhm.
Again, I mean. Right. Okay. So that's why we get two bromines here. And then it will keep going on. We repeat that.
Like more base attacks the alpha proton on the other side.
Yeah, on the other side as well.
But then wouldn't that bromoform leave?
Oh, bromoform leave. Let's see. X3. Let me see. Let me double check this.
The exam is basic. The name of the two chapters the exam is on is reaction at the alpha carbon of carbonyl compounds, enols and enolate,
Mhm.
and condensation and conjugate addition reactions of carbonyl compounds, more
Let's see.
chemistries of enolate. And that's
Uh-huh.
what we're testing on.
Let's see. Yeah. Oh yeah. And then later on, it leaves as CHBr3. And then
Mhm.
we have O minus O BR.
Okay, why is
But
there
let's
an O
see.
minus?
I'm trying to see the mechanism here really quick. Yeah. Haloform action mechanism. Let's see. Let's see. Okay. Where is the part where we get the cleaving? Oh, here. I see it.
Oh, the
Uh,
base attacks the
uh-huh.
carbonyl.
Yeah. Uh-huh.
Yeah,
That's right.
I just opened the textbook.
Oh, nice. It's been a while since I've seen this reaction. Let's see.
Are you
That's
taking higher chemistry?
yeah, advanced okay, I'm like grad level.
Oh my god. What the hell are you learning in there?
But I still need to know this stuff because I tutor like this undergrad level
The
outcome.
yeah.
Yeah. Yeah. It's good. It's good. This is a good review for me too.
You don't use that at all in your upper OChem?
Oh no, oh I haven't seen this since I've like taken this class, like the upper level
Oh.
outcome like didn't doesn't use this reaction. And then think of this right here as a good leaving group.
Hmm.
We could reform the carbonyl, the carbon of one oxygen, and then kick out that good leaving group by giving that carbon a negative charge right there.
In general, how do you tell if something's a good leaving group? Is it
Yeah,
because it's like
something.
electron withdrawing?
That's right. Something is a good leaving group if it's electron withdrawing, or it can do a lot of resonance. Because the definition of a leaving group is that it will leave with a negative charge. Because you notice how when we kick that group out, this group has a
It,
negative charge
because
now.
the three Br is basically pulling the electrons from that carbon-carbon bond.
That's right. That's right. Pulling electrons from that lone pair, making that lone pair of electrons stable. And if it's
Mhm.
stable, it's a good leaving group because it's able to stay as it is and doesn't want to go back and reverse the reaction.
Okay.
Right. So that's why this is a good leaving group. And we
And
will
then
have
there were conditions where like non-good leaving groups still leaves. I think like somewhere in the lesson, like OH also leaves.
oh yeah. OH is able to leave for aldol
Hmm.
condensation. And that's because in aldol condensation, we are in basic conditions. So there are other bases floating around in the solution. And also you add heat in the reaction.
So it helps the leaving group leave.
Yeah, so it helps the leaving group leave. It adds enough energy to make that bad leaving group able to leave.
Okay.
So it makes OH bad leaving group able to leave. Okay.
You explain why the basic conditions is important
Yeah,
for
the
leaving.
basic conditions is important for that bad leaving group to leave because when it leaves, it will leave as OH minus.
Hmm.
And the basic conditions, think of it as like other negative charges floating around. Those other negative charges floating around will kind of like support that negative charge in a way to make it able to exist.
How does it supportive? Does it
Oh yeah, it kind
like
of like
repel?
doesn't make sense because like like negative charges repel each other,
Yeah.
right? Yeah, so um
Or is it like overall the bases in the condition help like pull the leaving group off?
yeah, like it helps like rip it off, like pull it off.
Oh, okay. So
Yeah.
like the compound's already like pushing it, but then it's a bad leaving group, so normally it wouldn't leave. But
hmm
because it's in basic conditions, the bases around are like helping pull what's being like attempted to be kicked off.
That's right.
Okay.
And also for aldol condensation, it's required for you to be in basic conditions because you need to make an enolate ion for the reaction to happen. And to make enolate ions, you
You
have
need
to
basic.
need basic conditions to deprotonate the alpha carbon. Right.
Yeah.
And once we have this good leaving group, we have a strong acid here, the carboxylic acid. The very last step is that this negative charge will grab the hydrogen and deprotonate that carboxylic acid to get that carboxylate and this CHBr3, where the CH is this C and the H that it grabbed from that carboxylic acid. Like this
Okay.
H right here is that H right there.
Yeah. Thank you.
Mhm.
Also for if it's acid conditions, it would make an enol instead of enol.
Yeah, if it's acid conditions, it will make an enol right here. Um,
Mhm.
Instead of enolate, where in basic conditions, this is the enolate, the negative charge, enol. And
And that's
this,
because instead of pulling the alpha hydrogen, the oxygen is attacking a proton. in acid?
Oh, in acid here, the very first step, the oxygen here attacks the proton as the very first step in
Mhm.
acidic conditions. That's right. Because when acidic conditions, the very first reaction that happens is an acid-base reaction because that's one of the fastest reactions in OChem, acid-base reactions. So that's the very first step here. Protonate that carbonyl oxygen. But in basic conditions, we do not have an acid to protonate that carbonyl oxygen, but we do have a base, which will still do an acid-base reaction, but this base will deprotonate the acidic alpha carbon alpha hydrogen here.
Because the whole chapter is about how the alpha hydrogen is like slightly acidic, right?
Yeah, that's right. That's right. Yeah. And this question here is asking like benzoic acid after neutralization. This neutralization step is like after you get to this step, you just neutralize it by doing acid workup, H3O plus, to get to your benzoic acid or to get to your carboxylic acid.
No,
This
yeah,
is
the
not,
whole point of acid workup is basically to neutralize like the solution, right?
yeah, yeah, to neutralize that negative charge. That's right. That's right.
How come it's acid workup and not like basic workup? Like, do we normally not leave compounds with a plus charge?
Yeah, we normally don't leave compounds with any kind of charge where we do acid workup to neutralize negative charges, and things with positive charges will tend to neutralize themselves because there are like other neutral atoms around that would just neutralize that positive charge. But
Oh,
in
okay.
basic conditions, it will always end in a negative charge.
Okay, so you need like add some acid to give it a proton,
Yeah, and neutralize it.
and it'll
So,
make it an acid.
uh-huh. So, and for this part, see here, like this acetophenone is not like this thing right here. I did not draw acetophenone here. This is 2-pentanone. Acetophenone is something else. Let me see what that structure is.
Isn't it the phenol ring and then the carbonyl group and then a CH3?
Yeah, yeah, yeah. Acetophenone. Like that. Where after you do everything, you still get CHBr3 and you'll get this benzoic acid here after the acid workup, the benzoic acid, carboxylic acid next to benzene
Wait,
ring. This is not a benzoic acid, but it is a carboxylic acid.
base catalyzed. So basically, it's going through like the three alpha hydrogens one by one, making the bromoform.
That's right, that's right. Making the bromoform. And then in basic conditions, the base attacks the carbonyl, pop that double bond onto the oxygen right there,
And
and
then
then
it
repeat this
comes back,
whole
yeah,
thing.
and it comes back down and pushes the bromoform out,
Yeah,
and
yeah,
then
that's right.
you're left with the OH group.
That's right.
But then in basic conditions, it will also pull off that H, and
Yeah, it
then
will pull
you
off that
need
H.
acid workup to basically put the H back.
hmm That's right.
Okay.
That's right. You got it. After neutralization.
What about 3B? What
Let's
is
see.
the rack 3? Is that racemic?
Racemic. I think racemic, yeah. Why the racemic 3 bromo product forms as opposed to the alternative product? Oh, I think it's talking about like why we put a bromine here instead of here. You answered this earlier. You said the reason why we deprotonate this alpha hydrogen instead of the other one is because it forms a more stable eno. We didn't add another we didn't add a bromine here because that would have gone through the less stable eno intermediate.
Oh, wait, why is it called racemic?
Oh right, it's racemic because you know how there's a negative charge here, right? Like on that
Hmm.
carbon that's attacking it. This negative charge right here is sp2 hybridized. And if it's
Okay.
sp2 hybridized, it's flat. So when it attacks a bromine, it could attack on the top side or the bottom side, giving us
Hmm.
a wedge product,
Or a
or it could
dash.
have, yeah, or a dash product.
But then what happens if it attacks the other alpha carbon?
Oh, if the other alpha carbon attacks, then that wouldn't be racemic because that would not be a chiral center. Like, let's say,
Oh, because it has two H on it.
yeah, it has two H's, so we can't say racemic because not chiral center.
Okay, so basically it's asking why does it attack this carbon instead of the one on the left?
Yeah, uh-huh.
Okay.
That's right. Ooh, this one.
So I put I don't have sorry, I have both of them printed up. Yeah, I'm missing information. I think I said the bottom one is faster.
Yeah, that's right. The bottom one is faster because I'm going to draw out the carboxylic acid in its actual form, but I'm gonna draw out the top one in this kind of way,
Mhm.
where you notice how there's a H bond interaction going on right here that is very
Yeah,
stabilized.
that's what I
Yeah.
drew.
Uh-huh, uh-huh. So that's just gonna do that, and then do that. And then we get this enol form right here,
Hmm.
where this CO2 got emitted off as a
Yeah,
leaving group, as a gas. And then this enol here will just tautomerize back into its carbonyl form. Like this enol form will tautomerize into that
does
ketone
it
form.
need a reagent to do that, or
Yeah, it does. It needs to be either in acid or base.
yeah, okay?
But they didn't
But
give us any reagents. They just asked like which one would be faster and why. The reason why is because this carboxylic acid here
mhm,
is alpha to this carbonyl, whereas this carboxylic acid here is beta to that carbonyl. And the one that's alpha to the carbonyl can do H bonds and undergo decarboxylation. The one that is beta to the carbonyl cannot do hydrogen bonds and cannot do decarboxylation.
wait, so it can't come off at all? Like when does the top product form?
The top one is closer to the carbonyl, which is why it could do the H bond
Mhm.
more strongly and form the enol here. The top one right here can't come off at all. Like this is not possible.
Oh, so it's not even a top.
Yeah. This is wrong. No reaction.
Can it come
But
off if there's more heat?
with more heat, let's see.
Wait, let me see, because I think later in the lecture there is two carboxylic acid group and one is farther away, but the closer one comes out. But I think there was some point the second one came out.
That's interesting.
Let me see.
Yeah.
Maybe I'm remembering. Wait, so can you like overall go through like how you would answer that question?
Yeah. Predict which of the two competing reactions will be faster and explain. So I would choose the bottom one
Mhm.
because that carboxylic acid is alpha to the carbonyl and it could do hydrogen bonding with um the carboxylic acid and the carbonyl oxygen, where that hydrogen bonding can do decarboxylation and emit carbon dioxide. The top one here, this carboxylic acid is not going to be able to do hydrogen bonding with the carbonyl oxygen here because it is too far away. And if it's even like able to do so, it will not be able to form an enolate or eno ion because let's try drawing it out. Let's say we try drawing that decarboxylation reaction happening like that, where there's a, let's say they do have H bonds
Mhm.
and that creates a bond there. We do that. This bond here can't go here or can't go there because there's no sp2 atom to do resonance with to like pop off the double bond. Because you know how when we did this, we broke off this bond and then we put a double bond here, but we were able to do that because this carbon here was sp2. It was able to um like move this
Mhm.
double bond somewhere else. We can't make another double bond here because that would break the octet rule. these carbons here already has 4 bonds with hydrogens, and they can't do any more resonance. It's not able to
So
like
what would you call
go off.
those SP hybridized, not SP2?
SP3
Okay,
hybridized.
SP3. Oh, because
Right.
they have all four
Yeah,
total.
that's right. That's right. And these sp3 hybridized things cannot do resonance, so that's why this can't go off. It can't emit off as a carbon dioxide. Okay. Let's see. When compound C in ethanol is stirred with 1 molar equivalent of NaOC2H5 and 1 equivalent of CH3CH2CH2Br, a new compound D is formed. D is refluxed with ketone E is formed. Reverse the structure of D, and then the stepwise electron pushing arrow from C to D to E. Okay, let's do this mechanism. I'm gonna redraw it
Can I
because
ask you a quick question? Is
yeah,
C the product of Dieckmann's cyclization?
cyclization for like this reaction here is a cyclization.
No, the one before, like what form C? The question's not asking it, but basically
Oh,
the starting step was the product of Dieckmann's cyclization.
when compound C in
I
ethanol
basically
solution.
was doing this for practice because I realized that product is what
Oh,
we
this came
got.
from something.
Yeah,
Let's see. This probably came from.
I put that it came from um basically I don't really know what to call it compound. Is there a way I can draw as well?
Yeah, let me put on the whiteboard for you. Let's see. Right here. Okay. Yeah, you should see an annotation tool on the Zoom, like the if you're do you have an iPad or a tablet that you can connect the Zoom with? It's probably easier to draw there instead of the mouse or
No,
trackpad.
I have a tablet. It's not
Oh,
plugged
okay,
in
okay.
though.
Uh-huh.
Wait, would my mouse draw right now, or do I need to click on something?
You could draw right now. Yeah.
Okay. Where did I yeet that pen? Do you still have classes right now?
Yeah, I just started spring quarter. Like this is week 1 spring
Oh,
quarter. Yeah.
so I put that came from. Oh, it's not drawing. Do I need to click something?
Do you see the pencil tool somewhere on your screen, like the one of the corners of the
Oh,
screen?
annotate.
Uh-huh.
Draw. Should be fine. Uh, T. And then it came from this.
Oh, I see. Yeah. Okay.
Does that form the product or
Yeah.
compound C?
Yeah, this reaction that you're thinking of is intramolecular claisen condensation
No, I haven't listed at Dieckman's
or
cyclization.
Dieckmann. Yeah,
Oh,
Dieckmann
Dieckman's.
condensation. Yeah.
Oh, it's Dieck.
Yeah. That's another name for it, Dieckmann condensation, which is just an intramolecular claisen.
What did that mean?
Uh,
I reviewed
so
this like 3 times, but I forgot.
yeah, it's basically like an enolate ion attacking uh ester,
Mhm.
and then kicking out the leaving group that gets kicked out is a OR group. So let's do the mechanism here. Let's make sure this is the product. 1, 2, 3, 4. So the chain would have one more carbon, because we
Is it,
want to make a 5-membered ring.
isn't there
Oh yeah.
uh,
Yeah. I missed that. I missed that. One, two,
Yeah,
three,
you're in a little
four,
bad.
five. No, 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 no. See, okay, okay. Yeah, yeah. You're right. You're right. This is the reactor that it comes from. Where do you want to practice drawing the mechanism, like what happens in this mechanism, like the arrow pushing mechanism?
Oh, let me see what.
I could walk you through it too.
Can you give me a second?
Mhm.
I think it starts with this attacking basically the alpha hydrogen here.
Yeah, and I would draw out the hydrogen um to make it more clear, like this, draw the hydrogen, and then you know the bond between the carbon and hydrogen. That bond between the carbon and hydrogen is gonna kick off and go to that carbon right there, giving that a lone pair and
Oh,
what kind of charge?
uh, negative.
Yeah, negative charge.
Wait,
So yeah, yeah, there we go. Uh-huh.
is it necessary to write like the Na plus hangs out here?
No, 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 no. That's a spectator ion. It's you don't have to draw that out.
So when I write the reaction like this, can I just draw this instead of NaOET?
Yeah, you could draw it out like that. Yeah.
And then doesn't this attack this? I
Yeah,
forgot to draw the.
that's right. And what happens after that attacks that? Because
Would
that's
this have to go up?
yeah, that has to go up. That's right. And then the way I like to number is like I start my numbering from the attacking atom, and then I end my number to the atom being attacked. So we know we're gonna make a 5-membered ring.
This is the here, right? And then does this come back down and push the OR off?
Yeah, that's right. That's right.
So this would go, basically this comes back down and this goes out.
Yeah. And that's a bad leaving group. The OR minus group is a bad leaving group.
This OET right here,
Yeah, that OET is a bad leaving group. Which is why
but this is in basic condition, right?
oh no, that's for out of condensation where it's able
Oh,
to stay by itself. But for claisen or dieckmann, right? That
uh-huh.
OR minus will come back for its vengeance. Uh, so let's draw out the resulting thing, the resulting the
So
structure, and then
let's
draw.
draw a pentagon first. It's
Uh-huh.
easier.
Yeah.
And then OET comes out.
OAT
And then
minus.
this
Yeah.
on the first carbon still has the T.
That's right. And do you see any alpha hydrogen that is really acidic, like alpha hydrogen that's in between two
Yes.
carbonyls? Yeah, that right there, right, is gonna be taken by the OR minus that just left. It's gonna come back for his vengeance and grab that alpha hydrogen right
Oh,
away.
so this is gonna take this H.
Yeah, it's gonna grab that H, form the enolate ion, and then reform
Oh, it grabs this
the
H. This goes
carbonyl.
here and then this goes back up.
Yeah, yeah.
Wait, does it go back up on this one or does it go? Oh no,
So
it does go that one, right? Or
yeah,
does
we
it go
probably
with
let's go on that one
this one?
because there's competition for the other one.
Okay, so
Yeah.
this would end up with like that.
Right. And then from here, we just tautomerize it back into the carbonyl by reforming the carbonyl, and then that alpha carbon grabs a proton source from acid workup from the second step. So this is why we bring in the H3O plus workup step, where we reform the carbonyl bond, the carbon double bond oxygen, like
What
from the
else
negative
goes
charge.
back down?
Yeah, that comes back down. And then
Yeah,
the alpha carbon grabs a hydrogen from H3O plus.
like that. And then this will go here.
Yeah, That's right, that's right.
So this will go this has the H, and then this is our product.
Yeah, that's right. And I don't know if your professor's nitpicky about this, but all of these like steps are reversible,
Mhm.
except when we do this um Virgin step. When this bad leaving group grabs the alpha hydrogen, that's the irreversible step. But everything else is reversible. The Virgin step
No,
where
because
the
retrosynthesis. Wait, how does it go backwards? Like, does it just happen or?
oh like how does it go backwards? So
Yeah.
I'll 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 start from here and show you how it could go backwards to the original one.
Mhm.
We could reform the carbonyl and we could break this bond
Oh,
and
instead of the OET leaving, it breaks the carbon-carbon bond that just formed.
yeah, and then give it back to this carbon right here. That's right.
Is there a specific condition for that to happen, or is just the fact that it can go that way instead of kicking off the OET?
Yeah, it's just the fact that it could do that, and the reason why we don't draw that step in the mechanism is because that's not a productive step. It would just go back to like where it was. It wouldn't
Mhm.
change anything. The productive step would be like kicking out the OET and actually making something happen.
Okay. And then you said this step is irreversible.
Yeah, the step that's irreversible is like the vengeance step when the bad leaving group comes back to grab the alpha hydrogen between the two carbonyls. That's the irreversible step.
Is it because once it's grabbed it, it's out of basically the system,
Yeah, once it
and
grabbed it,
the hydrogen is not gonna randomly come back?
yeah, that's right. Because this is now stable, right?
Mhm.
Before this was very unstable. It's very, very reactive, very
Yeah,
unhappy. But once it gets to this form, it's stabilized and happy now. It doesn't want to go back to here. Like that's not good. So that's why it's
that's your okay.
irreversible. Yeah.
Oh God, there's so much to learn.
I know. But like you notice how like there's a lot of like fundamentals, like principles like uh the negative charge, bad leaving group, good leaving group, stuff like that.
Yeah.
See. Okay, let's go back to the
Oh,
yeah, problem. See.
oh, I also noticed you were recording. Are you sending me that recording?
Yeah. I'll send it to you afterwards.
Okay, thank you.
Yeah.
So I think some parts probably went too fast, and I need a replay to get it into my head.
Yeah. See. And also like if you have any questions when you're practicing,
Mhm.
just text me on like Discord because I'll probably get notifications from Discord more, and then
Do
I'll
I
reply to you on Discord.
still have you on Discord? What's your name on Discord right now?
Bryant.
Oh God, I
Oh.
just realized I have a message from you I never responded to.
It's like five almost 5 years ago. Oh, yeah, what the heck, Justin? Where's my response?
What the fuck was going on that day?
Late to the
I asked
party.
you if you want to play, and then you asked if I want to play next week on the same day as the response.
And then you just like left it on red.
Man, I
Oh
probably
man.
didn't read it if I didn't respond. I
That's
don't
fine, that's
normally
fine.
leave you already. I'm so sorry.
No, that's fine, that's fine. Yeah. Let's see. Okay. So, do you still play League or any games?
Yeah, I still play League.
Uh-huh.
That's like how I escape from reality.
Is that your favorite game, your go-to game, or CS?
I uninstalled CS for space for Genshin, but I
Oh,
haven't even
Genshin.
played Genshin. I've mainly been playing League for like
Yeah,
eternal
yeah,
reasons.
yeah. Uh-huh. Okay. So, what do you think the very first thing is gonna happen here? We have uh
The the what is the group called?
ethoxide.
The dark side
Uh-huh.
is gonna attack or basically grab the alpha photon hydrogen,
Mm-hmm.
and then um the propyl is gonna go there.
Mhm. Oh yeah, you could draw it in this form, or you could draw the negative charge on the carbon, um, like that. And what do you think
Oh,
that
so that
negative?
saves a step of drawing. Like you don't have to go into enolate and then come back.
It's probably safer to draw in the enolate form because that's more accurate. Like it's more stable as that form, and most professors draw in this form. So let's stick to the safe route.
Oh, so draw it out and then draw it basically coming back to the lone pair, or
Yeah, well, we don't have to draw it back to the lone pair. We could just say that that's a lone pair right there. That's going to attack something. What do you think that lone pair on this carbon is going to attack? Once we have this here.
basically the whole thing except the bromine because bromine is negative ion. Right?
Yeah, well, not the whole thing. There's one atom that's electrophilic. It's the atom directly attached to the bromine.
The carbon, yeah.
Wait, wait. And I star that one. I dot that one. Star the attacking atom. Dot the atom being attacked.
Mm-hmm.
And we get this one, two, three. Star atom dot atom. This right here is a new bond
Mm-hmm.
between the star and dot atom. And we see that the atom is attached to one, two other carbons, one, two other carbons right there.
Yeah.
Okay. So now, do you know what kind of functional group this thing is?
And ester.
Yep, an ester, that's right. And once we put an ester is a carboxylic acid derivative. If we
Mm-hmm.
put that derivative through an acid or base, it goes through a hydrolysis reaction. It converts back to the carboxylic acid. Right?
You show that.
Yeah, where the first step here is that the carbonyl oxygen is going to get protonated by the H3O plus,
Mm-hmm.
and oh, I need more space. This is kind of long. Let's see. I'll just go here. Okay. When that happens, protonated. Now, this is an activated carbonyl carbon. Before, this carbonyl carbon had a partial positive charge, but now that carbonyl carbon has a bigger partial positive charge because this is an activated carbonyl now with the positive charge oxygen. Right?
So the water is gonna attack.
Yeah, that's right. So now the weak nucleophile water is able to attack that activated carbonyl. And this right here is going to be our proton transfer step now, where we want to proton the group we want to leave and deprotonate the group we want to stay. Since we want to make a carboxylic acid, which group do you want to stay and which group do you want to kick out?
Uh, the water, the top stays and then the bottom one gets kicked out. Right?
That's right, that's right. Since we want this to stay, do we have to deprotonate or protonate this group?
The protein.
Yeah, deprotonate, that's right. And we could use water to deprotonate it to make it into a bad leaving group. Now we want this group to leave, so we want to protonate to make it into a good leaving group. So instead of memorizing like every single exact detail without like understanding it, when you do these mechanisms, try to talk to yourself through each arrow and explain why that arrow is doing what it's doing, and
Mm-hmm.
it will like be easier to remember what's going on for these mechanisms, like why you deprotonate that group, why you will protonate that group, and what you're trying to go to.
Okay.
Once we have that good leaving group, we're gonna have this oxygen reform the carbonyl and just kick out that good leaving group.
That just happens on its own.
Yeah, it just leaves by itself after we reform the carbonyl right there. Because once we form that good
I
leaving
meant
group,
the reforming of the carbonyl. That happens by itself.
yeah, well, it happens with the living group leaving because it's able to do that because we had a good living group. If there were no good living groups, like let's say these were H's and these were R's, it won't be able to do that by itself because there's nothing to kick out. But there is something to kick out, so it's able to happen. Like if this wasn't there or this
Mhm.
wasn't there, then that wouldn't be able to happen.
It would just stay as a alcohol.
Yeah, that's right.
So those electrons can come back down even though there is an H attached to it and it's stable.
Yeah, that's right, that's right.
Interesting.
And that H is still there. And this oxygen there with three bonds will have a positive charge,
Mhm.
and this is the leaving that left. Uh, all we have to do now is neutralize that positive charge by deprotonating it. And what do you notice about the relationship between the carboxylic acid and the carbonyl? Is this carboxylic acid alpha or beta to the carbonyl?
Beta.
Oh, so this is the carbon right here that's holding the carboxylic acid.
Yeah.
How many carbons?
So you're counting that one?
Yeah, that's right.
So it's
So
alpha?
yeah, alpha, that's right, because the alpha carbon is holding the carboxylic acid. If it was a beta carboxylic acid, it would be on this carbon right here. Right. So I'm going to redraw this alpha carboxylic acid in this form. Um, I'm gonna move this R group somewhere else like that, and then I'm gonna do that like that. What do you notice here that we did recently that's very similar?
Like an
What?
H bond?
Yeah, And with the heat, it will do decarboxylation,
Mhm.
and that would be OH, that, and like that. Let me see. Yep, that's what they want. Okay. 1, 2, 3, 1, 2, 3. Okay. Now we're in acidic conditions, so
It's
we're
gonna
going
grab the
to
H.
want to protonate one of the carbons here. Which carbon will give us the more stable carbocation? Which carbon will have the more stable positive charge?
Is that the one on the right because it's more substituted?
Oh, yeah, the one on the right is more substituted. Like there's more carbons around it, but the one on the left has two carbons around it and an oxygen
Oh,
next to it. The oxygen next to it has lone pairs that is gonna make it more stable because the positive charge here is able to be stabilized by resonance by the oxygen,
oh,
right? So that means that this carbon here is gonna grab the hydrogen from the acid, right? When that happens, right, this wait, no, no, no. That carbon grabbed the hydrogen. This carbon lost the bond. This carbon lost the bond, which is why it has a positive charge. This carbon gained the hydrogen, which is why it's still
okay.
neutral. And then from here, this oxygen with the lone pairs is just gonna come down
And
and
reform the carbon.
yeah, we form the carbonyl. Last step.
And then the water that was left from the double bond grabbing the proton will
Mm-hmm.
grab that. Okay.
Yeah. And neutralize. 1, 2, 3. There we go. So this right here was a hydrolysis step first, and then it went to a decarboxylation. For this one, this was
What's the definition of hydrolysis?
hydrolysis was um turning a carboxylic acid derivative,
Uh-huh.
which
Into
is either an acyl halide, anhydride, ester, amide, or it could be nitrile. Any of these things, if you put that through acid and water, it always goes back to a carboxylic acid,
okay.
to a carboxylic acid. For this one was an acid base reaction to form enolate
Mm-hmm.
and then SN2 reaction. Okay. Yep. Any other questions?
Would you be able to go to the last page? I know we're out of time.
Oh yeah. You want to go over it tomorrow? Like I could do this like last page tomorrow for tomorrow's session.
Okay.
Yeah. Uh-huh. But I'll send you the recording for today's sessions because I'm planning to like sleep early and wake up early tomorrow.
Would you better quickly go through E though, like how you would do
Uh-huh.
E?
E. Yeah. Let's
Yeah.
see. Ethyl acetate diester or food synthesize. Okay, let's draw this E out. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. Ethyl acetoacetate or ethyl melanate, benzene. See, let me see what this is. Ethyl.
Do you have a tip to remembering basically the name of reagents and groups?
I'm not too good with nomenclature. Like
Uh,
I have to like
because the first page of the exam is straight up nomenclature.
oh really?
Yeah, he gives you like 10 names and you have to draw it.
Oh my God.
And then last exam, he was like, if you don't know this one, it's a straight zero.
Oh shoot.
Because
That's so
he's,
mean.
yeah, because he stresses like, how can you do OChem if you don't even know like what you're working with?
You can just search it up.
Or, like, when am I doing OChem?
Yeah. Let's see. Benzene. Okay. No, that's not good.
Oh, also, how is this gonna work if there's more people?
Oh, yeah. So, when there's more people, it's probably gonna be more like yeah, UC Davis, OChem related. Um, so it's probably gonna be like this week only where I could do like one-on-one with you. But
Hmm.
because I also do private tutoring. If you're interested in private tutoring, let me know. Because I have I have like packages on it, and
Hmm.
like if you're interested in that, then just let me know. But then this week we're here is like probably one-on-one time with you. Because like week 2 is when like probably UC Davis students are gonna come in more.
Okay.
Uh, Let's see.
How do the packages work? Like, I pay you and then we get more one-on-one sessions,
Yeah,
or
and
how's that?
then you schedule sessions with me anytime you want based on my Calendly on my available time. And then we have those sessions. It doesn't have to be this time. It could be anytime you're free and matches up with my schedule as well.
Okay. And
Mhm.
it's payment per session, or how's that?
So the package is prepaid, so you could pay ahead of time for 10 sessions and then it's set like 10 sessions, or you could like
Hmm.
pay one at a time. I'll send you all the
Okay.
information after this session.
Okay. Thank you.
Mhm. Yeah. But this week is probably one-on-one, like with just me and you only for like the 9 to 10 one.
Hmm.
Yeah.
My library, like, they also offer tutoring, but I don't know what to expect or like what to bring and stuff like that.
Mm. Oh yeah, what to bring and stuff. Like the questions and stuff like that.
Yeah. Because I think overall
Uh-huh.
I'm at a zero baseline.
Let's see. Okay. Nothing available ethyl acetate with 3 or fewer carbons and any inorganic reagents show how to synthesize the following. Okay. This is interesting. So this is 1, 2, 3, 4, 5. To there. Let's say this came from that. No, that won't work. Let's see. I'll get back to you on this tomorrow.
Okay.
Yeah. This is this the stump me. Yeah.
I can
I'll get
also
back to you
ask
this.
my workshop leader for the answers. I just have
Yeah,
to
but
go through it.
yeah. Let's see. Diethyl acetoacetate. Anything? Yeah, because I'm trying to use like these things here, but I'll see.
Mhm.
I'll see. I'll work on it, and then I'll see you tomorrow and work on it.
Okay, thank you.
Yeah. And then you get the answers from your workshop leader to double check, please, as well.
Mhm.
Okay, sounds good. Sounds good. Yep. I'll see you, Justin.
Thank you. This is
Yep.
very helpful.
Sounds good. Sounds good. See ya.
See ya. Good night.
Night.